right, continuing on with energy, we're going to talk about mechanical energy today. We're talking about spring energy, potential spring energy. So we're going to finish up the idea of energy. Conservation of mechanical energy. Oh, I guess I need to hand out notes, don't I? That would help. Well, sitting there looking, where's my notes at? When a quantity is conserved, it remains constant over an instance of time. When a quantity is conserved, it will maintain to be the same energy over the entire time. Which means our mechanical energy initial has to equal our mechanical energy final. Forms of mechanical energy. Forms of mechanical energy. Kinetic energy and all forms of potential energy, whether gravitational or elastic. These are types of mechanical energy. Forms or examples of non-mechanical energy. Nuclear energy, chemical energy, internal energy, thermal, electrical energy, and thermal energy, which basically is friction. These are non-mechanical energies. When things are moving, when things are in motion, as that is mechanical energy. But when you start throwing in the idea of friction, this turns into non-mechanical energy. If you take a paper clip and you continue to bend it back and forth, back and forth, back and forth, or you take a coat hanger and continue to bend it back and forth, okay, eventually what happens to the coat hanger, or what's going to happen to my paper clip here? Yeah, it's going to snap. If we take a look at the point where it snaps, or where you're trying to bend it and continue to bend it, what happens? What does that feel like when at the point where it breaks? Yeah, it gets hot. It gets hot. This paper clip warms up right where I broke it. What is happening there is the non-mechanical energy you have a bunch of bonds that are in there that are being broken. Every time that you bend it, it breaks, or it continues to break these bonds. Eventually, it entirely breaks the bond. Well, what you have there is you have heat energy that's going to come out of there. That is the breaking of the bonds that are in there that holds these things together. If I just bend it and I bend it back, probably not going to have mechanical energy, too much mechanical energy that's going to be lost. That's what we call elastic energy. A rubber band will bounce back and forth. Okay, it will continue to bounce back and forth, and that's called elastic energy. Eventually, if you pull too hard, it's going to break. Okay, it breaks the bonds, and then we start turning into non-mechanical energy. But when you talk about kinetic energy and potential energies, all those things are going to be mechanical energy. The biggest thing that occurs that takes away these energy is this thermal energy called friction. That is what dissipates a lot of our mechanical energy. Because if I'm pushing a desk across the floor, okay, I have friction that is there. Okay, the amount of work I put in is not going to be the amount of work that comes out. Why? Because I have a forced net. I have a forced net that's going to give me the net work coming out, and it's not going to equal the amount of work that I put into it. We push a block, and we've worked on a couple examples and did a couple problems where you pushed on the block, and you found how much work you did. But then you had the work of friction that took away some of the work that you did. Okay? So you have this deficiency of the amount of work that you did because of friction. In the presence of non-mechanical energy, mechanical energy is not conserved. In the presence of non-mechanical energy, your potential or your mechanical energy is not going to be conserved, which means your mechanical energy that you put in is not going to be the same as the mechanical energy that you get out of it. Okay? You have to overcome friction. You have to overcome friction to be able to push a box or push something across the floor. Our net work that's happening is not going to be the same as the amount of work that you put in. That friction is going to dissipate the mechanical energy that you have. We talk about elastic potential energy. Elastic potential energy. Springs. When spring stretches or compressed, energy is conserved. When I take a rubber band and stretch it out and allow it to relax again. Mechanical energy typically, or the potential energy, mechanical energy is going to be conserved. Okay, because it's just going to go back and forth. It's going to bounce back and forth. In your car, you have springs underneath your car that support your car and the frame of your cars. Okay, they are things that will continue to absorb a lot of your shock when you hit things. Okay, those springs will conserve the mechanical energy. Okay, they're built to conserve the mechanical energy. So when you stretch or you compress, energy is stored. Okay, when you stretch something out, you store some energy. When you compress a spring, you store some energy. Because think about what we've talked about. Okay, we have work that's being done. We are taking a force and we're exerting it. If we take a force and we exert, on a spring. We take a force and exert on a spring. Work is being done. And work, once again, is equal to your change in potential energy and your change in kinetic energy. So your work that's being done is equal to your change in mechanical. Your net work is going to be change in potential, change in kinetic energy. It's what we've talked about already. If I am stretching a spring out, I'm taking a force and exerting it for a distance. That means I'm doing work. That means my potential energy is changing. What I had initially with my potential energy, I have changed it. Why? Because I've done work. So I need to have a change in potential energy. Okay, I need to have a change in energy because I've done some work. I've done some work to stretch something out. So there's still a direct connection to the amount of force that we've exerted for a distance and the idea of work going into energy. Well, this is going to be stored energy. Okay, it's going to be stored energy for the object, whether it's a spring or it's a rubber band. The force exerted on the spring, the force that is exerted on a spring will be directly proportional to the displacement of the spring. The work exerted on the spring will be directly proportional to the displacement in the spring. If we're directly proportional, this is also a direct variation from your trig days. When dealing with your trig days, it's a direct variation. And if you look at a direct variation, remember the direct variation function. It is a linear function. This is a linear function that contains the origin. So when you talk about a direct variation, it is a linear function that contains the origin. And direct variation is the same thing as directly proportional. As one increases, the other increases at a constant rate. So what our graph will look like is our displacement delta x or d, and my y-axis is force. They're directly proportional, which means I'm going to get a line. So our force is going to equal some constant time of displacement. So force will equal delta x, or k times delta x or d. We have a constant times displacement. Now the spring constant K is a parameter that measures the spring's ability to or resistance to being compressed or stretched. And it is a different value for each spring. So when you have a spring constant K, is a parameter that is a measure of a spring's resistance to being compressed or stretched. This constant is a constant for each individual spring. Some springs will be really stiff, some will be really stretchy. Rubber bands, some are really stiff, and then some are really stretchy. Depends on the thickness that you have there. So when you have a spring constant as a parameter that is a measure of a spring's resistance to being compressed or stretched. And once again, it's individually per spring. And things that we will get into in calculus, once again, the direction, what we've talked about, there's a direct connection between the idea of calculus and physics. Calculus was developed to be a mathematical explanation of physics. Okay, mathematical explanation of physics is done through calculus. Well, we've dealt with the idea of derivatives in calculus. The undoing of the derivative, which we sort of touched on a little bit today, using the idea of a differential, is called an integral. It is the undoing of a derivative, is the antiderivative. So if you take the integral of force, this results in work. The integral also has a second meaning. It is the area between the graph of a function and the horizontal axis over an interval. The integral is the area between the graph of a function and the horizontal axis over an interval. So this work is the integral. This integral is the area. Okay, so work is the integral of our function, but that integral is also an area over an interval. Well, if I take a look at an interval here, here's my interval, my delta x. Here's my graph of the function. Okay, the integral is the area between the graph of the function. Well, here's the graph of the function here, and the x-axis, which is here, over an interval. So what we're looking at here is this area right here. Well, what I have just shaded in is a triangle. This is just a triangle. Well, how do we calculate the area of a triangle? See? 1/2 base times height. So the area of a triangle is 1/2 times our base times our height. Just the area of a triangle, going back to geometry. Well, if we take a look our base is delta x, and our height is some force at this last value. So the force that exerted to stretch it, I get a delta x. We have a spring in here. I exert a force. I exert a force to stretch it. Okay? I exert this force to stretch. Okay? I have a delta x. Here is where I start out initially. If I start out at 0 there, then I stretch it out. I have moved the spring and I have stretched it out a certain amount distance. Okay? Well, that's my delta x, so I've moved my spring. My delta x is what my movement is there. The force I exert gets me to this point. Okay, so I'm exerting a force to stretch something, a delta x. So we exert a force F to stretch my spring delta x, or distance. Well, if we take a look at this triangle, my base is my delta x. The force that I exert to get this delta x is my height. So what this converts into is 1/2 times delta x times F. One half F delta x, which is the area of the triangle, which will then translate into this is going to be the work. The work is being done. So we have 1/2 force times delta x, because that's the area of our triangle. Our force, once again, is defined to us as K delta x. Our force is K delta x. So making this substitution into here. We're left with 1/2. We're left with work is equal to 1/2 K, and then we have delta x, or 1/2 K delta x squared. Work is also defined to us as a change in potential energy. Work is defined to us as a change in potential energy, which is potential energy initial minus potential energy final. Well, if I'm not stretching the string at all, if I'm not stretching the spring at all, how much potential energy does the spring have? 0. Okay? So initially we have no stretch of the spring, so we have 0 potential energy. So if the spring is not stretched, our initial potential energy is 0. So my delta PE, my change in potential energy, is just your final potential energy. Which is the work that's being done on the spring. So potential energy for a spring is equal to its work, which is 1/2 K delta X squared, or 1/2 KD squared. And this D is how far did you stretch? Okay, how far did the spring stretch? That's what you're looking at here. That D is just how far did the spring stretch. Once again, these are things that you should add to your sheet. Hopefully you have work is equal to delta PE or delta KE. And then potential energy for a spring, or the work done on a is equal to, your potential energy of the spring is equal to the work done on the spring, and work is equal to 1/2 K X delta X squared, or D squared. Again, those are things you should have. Force is equal to K delta X. A mass of 20 kilograms stretches a spring 54 centimeters. What's the spring constant? Force is equal to Kx, or delta X, does not matter. Throw a delta in there. Force is equal to K delta X. You have a force, a weight that stretches the spring 54 centimeters. what is the spring constant? Well, we have a 20 kilogram mass. How can we do a force with a 20 kilogram mass? Bennett, what should we do? We have a mass of 20 kilograms. What type of force? How can we calculate the force for that 20 kilograms?
Do the displacement divided by order.
How can I find a force? What's the force that's exerted on this? But that's a mass. How can I convert the mass into the force? Gravity, yeah. It's weight. Calculate its weight. Why don't we calculate its weight, Jordan? Huh? Yeah. We can multiply this by its gravity. So we can multiply our force of gravity is going to be the weight, 20 kilograms times 9.81. So the force that's being exerted here is what, Tess? And those are in figs. Okay, now, when you're talking about a spring constant, okay, most of the time your K value is going to be in Newton per meters. Most of the time, they will be given to you in Newton per meters. That will be your spring constant. So if I want to find my constant here, I could take my force and divide it by my delta x. Well, my force is 196.2 newtons, and my displacement, my delta x, is in centimeters. So I need to convert that into meters. .54 centimeters, Liam's in what meters? 0.54 meters. So we have the 196.2 divided by 0.54, and we can find our spring constant. Brandon, what do you get? 360.3. And that's newtons per meters. Calculate the potential energy of the spring when it stretches 54 centimeters. Well, potential energy, once again, is the amount of work that's being done. Initially, the spring does not have any potential energy. It's just sitting here, not stretched out. Now it's stretched. It has energy. It has potential energy. Now, once again, it's stretched out here. It has potential. Okay, the potential energy is for it to go back up. Okay, that's the potential energy. It has potential to go back up. If it's just sitting here, there's no potential in it. It's just sitting here. Once I stretch it out, there is potential for it to move. So if I let go of it, the potential for it to move, it goes back up. So the potential energy, that potential energy is also sometimes called stored energy. it's stored in the spring, it's stored up energy. I had to do work. My work that I did has now stored up in that spring. Okay, I've done work and I've stored it in that spring. Well, we can calculate potential energy as 1/2 K delta X squared. So we have 1/2 363.3 newtons per meters times our delta X, which is 0.54 meters squared. Anna, what did you come up with? 52.97. What's our units? Joules. Because we have a Newton per meter times our meter squared. One of the meters will cancel out. So we have a Newton per meter, which is a joule. Or a Newton meter, which is a joule. So that's how much energy has been stored up. It's also the amount of work the weight did. That's the amount of work that gravity did. What I would like you to do for homework, okay, you had on the problems that we did for today, or for yesterday, we had that one problem about the spring that you weren't able to do. I want you to go ahead and do that problem now. Okay, you'll be able to do that problem now. If you want to, work on this. We'll work on this tomorrow also. The Great Pyramid of Khufu in Egypt has a height of 147 meters, side slopes of 52 degrees with respect to the ground. Stone block with a mass of 1,370 kilograms were used to construct the pyramid. Begins to slide from the top. Coefficient of friction 0.45. Calculate the kinetic energy and the velocity of the block at the bottom of the pyramid. I know it does nothing to do with springs. I get that. I want you to work on that spring problem first. If you have time, give this a little look at. Questions? All right, we have pretty much completed the chapter, so we'll start steering towards quizzes and tests for this entire chapter.